get into metabolism and detoxification. So this is a really big, important role. And I think most people have heard your liver does the detoxing. But what does that actually mean? Well, when you look at what the liver does, the vital role is the uptake and processing and distribution of nutrients. So it's sort of like the hub of the like where the proteins and the carbs, which we've ingested, they've gone through the GI tract and they've gone into the portal vein. And fats, by the way, go via the lymphatic system. But all those nutrients, proteins, carbs, and fats, all end up in the liver at some point. And the liver can regulate what happens, not just here, but in other structures of the body. So again, we're going back to that being interconnected. So for instance, the adipose tissue, that can receive a signal from the liver to release glycerol and fatty acids. That will happen. Skeletal muscles, they can release lactate or pyruvate and some amino acids. Incidentally, that they can't release glucose. That's a very interesting fact, actually. So we'll just add that quickly. I wasn't going to talk about that. But muscle cells skeletal muscle cells cannot release glucose, okay? They can store it as glycogen and they can use it for energy, but it can't leave the muscle. And why is that important? Because the only place where glucose can actually leave tissue and be delivered to other parts of the body is the liver. So this is where people get a little bit hung up on their blood glucose going up and wonder what the liver's doing. But let's actually pin that down with a bit more detail. So the liver can decide to release nutrients. And when you talk about glucose, everyone talks about gluconeogenesis, which is one of the functions, but actually there's a thing called glycogenolysis. So that's where your glycogen, which is the stored glucose, is lysis. If you ever see lysis on the end, that just means it's being cut. So what's happening there is the stored glucose in the liver is being cut. And normally that tends to go to the brain and the kidney. And gluconeogenesis, which is new genesis, the formation of glucose, is from non-carbohydrate substrates, so like amino acids, alanine, and things like that. So, but also fatty acids, lactate can also make glucose. So it's really a fantastic organ. The liver can release acetoacetate, which is produced through beta oxidation. So that's where you're getting into the fat burning and ketones and those sort of things. And also it plays a role in carbohydrate metabolism. And this is where we start to have problems if you have too much carbohydrate. And this I'm trying to make as simple as possible. So let's talk about it. So when you have carbohydrates, they're broken down by the saliva, which has got the amylase in your mouth, and that breaks it down. There's also a little bit of amylase from the pancreas, which breaks it down in the intestines. But I tend to talk about the first hit because it's very easy to say the mouth does the carbohydrates, stomach does the amino acids and proteins, and the small intestine does the fats. That's very general, but it helps to understand. So let's have a look at that glucose. So it's been broken down. It goes to the liver via the portal vein, remember? Now, the liver has what's called finite storage. So we know this. We know that the storage is up to 65 grams approximately of glycogen per kilogram of liver tissue. So that's it. So if you've got an excess of glucose, it's not getting there. It's not going where it can be stored as glycogen. That's a fact. That's studied, known. What will happen to that? Well, it will be delivered to the adipose tissue, to the fat tissue. And that's what happens. It will be delivered as fat, but also within the liver itself, you've got this manufacturing of fat. And synthesizing fat is primarily done in the liver. So if you're overloading it with glucose, you're going to up the production of fat. Now, the fat metabolism, so this is a big problem because we're talking about a macronutrient as fat. We seem to think that fat makes fat, but actually it's broken down. It's already gone through the lymphatic system, and the liver will actually not make fat out of that, believe it or not. It will, it will convert fatty acids and glycerol to triglycerides as a storage in the adipose tissue, or it can be converted into ATP or ketone bodies, which we know about and utilize for energy. So those pathways are very different, especially if you're fat adapted, which hopefully you are as a kind of, or you'll become that. This part of the fat production is going to be utilizing it for energy in the form of ketones. So it does seem to be the biggest culprit for fatty liver. We haven't talked about another one, which is fructose. We're just talking about the main macronutrients, but it looks like glucose is going to have the hardest job. And we could also talk about fructose at some point, because there does seem to be an association with fructose and the accumulation of fat in the liver. That's for another day, because I want to keep this as easy as possible and talk about the three main macronutrients. And then you've got the protein metabolism in the liver. So amino acids, they're broken down in our bloodstream. They can enter into tissue and turn into, sorry, I got a scratchy bit there. They can go into tissue and they become structural proteins, which is often what I say in the meetings, but I want to actually give you a little bit more, because now you're in this space, I think we can get a little bit nuanced. So what are structural proteins? Well, I always sort of say hair and nails and all that sort of stuff, but the underestimated things are enzymes, for instance. That's right. All the enzymes we talk about, all made from protein metabolism. What about hormones? Yeah, amino acids are used in the manufacture of hormones. Excess amino acids then go to the liver and they're processed. And during this processing, the liver will release ammonia and glutamate and glutamine and aspartate. And that's important because we talk about the kidney health and urea, and we talk about the breakdown of protein. Well, what I just mentioned, one of the breakdown products is ammonia. And again, this is all going to tie up with the bloods. So ammonia becomes uric acid. Yeah. So when you are eating a lot more protein, that can go up slightly. Don't be scared of it, because it's an antioxidant. And some of that uric acid can become urea. So when you talk about the blood urea nitrogen reading on your bloods as a carnivore, yes, it's going to be higher because there's more protein. That's why. And ultimately, that will become urine. So that's part of the metabolism of proteins. That's why when you do a blood test or a urine test, you can find that the urea nitrogen is slightly higher, because nitrogen is what amino acids are made up of. So the liver is doing a detoxification of nitrogen. It's not a big issue if it's in your urine. That's actually a tick. That's a success. It's done its job. So that's one of the things that protein does. But the other thing the liver does is it produces coagulant proteins. So proteins that bind to something else. So don't think of coagulation just as like blood clotting. There's many other things. It's just like a binding. So transport proteins like albumin, that's a protein that lumps itself onto something else, or something else lumps itself onto it and it gets transferred around. You've also got copper and iron binding proteins, which is really big when you talk about regulation of heavy metals and iron, particularly in your body. You've got protease inhibiting proteins. So proteases break down proteins, and believe it or not, you need another protein to inhibit that. So proteins work brilliantly together on structure. So that's the whole metabolism of the liver when it comes to the three main macronutrients. You also got detoxification of xenobiotic metabolism, is a posh term, but basically that's things like cigarette smoke, pollution, pesticides, all those sort of things. That happens in the liver. There's, well, it's well known to have two pathways to do this detox, and one is cytochrome P450, which is phase 1 detox, which is sort of more serious detoxification, basically trying to keep this really basic. And phase 2 is where it takes a toxic compound and makes it a little less toxic and then excretes it. So that's why when you do urine analysis, you can actually work out what's going on in the body. So that's that. But what about red blood cells? You see, this is another thing, the metabolism of red blood cells. This is going to tie into the HbA1c. So HB stands for hemoglobin. A1C is the type of hemoglobin. There's A1, A2, and there's different ones, but we always talk about HbA1c. But now I'm going to broaden it out, just talk about hemoglobin. So that word is two things joined together. Heme, which is the iron portion of the hemoglobin, and globin is a protein portion. See, so when you've got hemoglobin, it lasts in the blood, we reckon about 120 days. Although I do think, and I've been talking about this for a year now, when we're looking at bloods, and I'm now seeing so many bloods from carnivores and looking at their daily blood glucose and their HbA1c, their daily blood glucose on average is much lower, and sometimes their HbA1c is a little higher. And my supposition, and I think I'm the only one saying this, I have heard Dr. Sywest mention this, I think, is that maybe those red blood cells, because we are now eating a more species appropriate diet, maybe those red blood cells are lasting longer. You get the slightly more glycation, but every other part of it is still usable. So anyway, that's an aside. Anyway, right. So you got the heme and you got the globin, and that they've been broken down. The globin gets recycled, it undergoes amino acid catabolism, and it gets utilized elsewhere. You see, this is what I'm saying. The body is amazing. And then the heme part from the red blood cell, that's taken apart, and it eventually, I don't want to give you the whole pathway, but it eventually becomes what's called bilirubin, which is a blood marker that we can look at if you have problems with the liver. That's why, because it makes bilirubin, and that goes into the liver. It's conjugated in the liver, so it's bound to a protein, and then it will eventually be excreted. And I just want to explain this because I often talk about the color of your urine being really important, and it should be yellow. So this bilirubin actually becomes urobilinogen, I think it's called, actually. So really going back into my training here, and that goes to the kidneys for excretion, and it's yellow. You know, that's why we want your urine to be yellow, because that shows that's working. So straw colored is probably a better word, but in textbooks tend to say yellow. Or it goes back to your intestines for excretion. So can you guess what that means? If it's going into your intestines, it's going to go into your colon, and it's going to come out another way. It was a bit more solid. And that's actually why your poop is brown. And if you have a problem with liver and bile production, it can look yellowy. See, so it's all explainable. Now, if you have liver damage, those processes of urine and feces can be compromised. So where does that yellow go? Well, it goes into your skin. That's why you get yellow jaundice. So your peripheral tissue turns yellow because it's not being peed out and it's not being pooped out. And that's really that simple. So it's a really good marker that you've got a liver problem or jaundice if you've got yellowing of the skin, yellowing of the whites of the eyes. But that's the reason that we talk about that. But you can see it's a big subject, and I think it's worth it, because if we can do the whole process, and why it's important, I think I'd rather do it in one chunk